Welcome viewers to this session on Galerkin weighted residual method for the course Finite Element Methods for Beginners. So Galerkin weighted residual method is used to solve field problem or to develop the element equation for the field problems like heat transfer problem or CFD problem. In this, we will start with the general approximate method and one of the most common approximate method, Ritz method. And then we will introduce Galerkin method and try to develop finite element equation using Galerkin method. So let us begin our session. So the approximate methods are used for finite element formulation as such, but the approximate methods can also be used without finite element method. So one of the most important approximate method is Ritz approximate method. We have the variational method that is called as Rayleigh-Ritz method as well, and this is Rayleigh-Ritz method, that is variational method, and it is weighted residual method. So if we consider that a problem is defined by a function of phi x that is equal to 0 in domain omega, where phi is the field variable and is function of x only, and omega no doubt represents the domain, and it satisfies these boundary conditions on the boundary, and boundary conditions are given by the first boundary condition may be g1 of phi of x that is equal to 0 on boundary first, and the second boundary condition may be given on the second boundary, or there may be n number of boundary conditions. So in case of approximate method, we assume the solution. So solution, let us assume this solution as phi dash, which is the assumed solution, as phi dash function of x and some arbitrary constant a1, a2 up to an. This implies that phi dash is a function of independent variable x and the constant a1, a2, a3. So we can write down this assumed function as a1 n1x plus a2 n2x plus an nnx. So in summation form, we can write down this phi dash is equal to I is equal to 1 to n terms that we are using for this approximate function nix. So this assumed function solution satisfy the boundary conditions, and this function nix is called trial function because this is the function on which this phi value of phi dash is depending, which is the assumed solution of the problem. So if we are doing first order approximation, then we will use only n is equal to 1. It means it is first order solution, first order approximation. So in case of first order approximation, so in case of first order approximation, phi dash is given by a1 n1 x, and in case of second order approximation, n is equal to 2. Expression phi dash will be equal to a1 n1x plus a2 n2x. and so on. We can go on and on for this. So trial function must be continuous and differentiable up to the highest order present in the governing equation. So if my governing equation is second order, then n1 and n2 should be differentiable up to second order, and it should be continuous. If it is continuous, then only it will be differentiable. So when this assumed function, this general function, the general assumed function is substituted in our governing equation, then because it is approximated, so it will not satisfy it exactly. It will not be equal to 0. So what we get is known as residual. So if I substitute here in this function, I will get f of phi dash x. So what I have done, phi I have replaced with phi dash. It means I have substituted this function field variable, values of field variable or the relation of field variable in the differential equation governing the solution domain. So this will give me not 0, but now this will give me some residual, and this residual is represented by R, and it certainly will be function of dependent variable and a1, a2, that the constants that we have used in the trial function. So in the Ritz method, for the first order approximation requires that integral of residual with respect to x be 0 over the domain omega. So it means what, if I am only talking about a1 term, it means for the first order, I am just taking example of the first order to make it slightly simpler. We can go on and on for second order, third order, and so on. In case of Ritz method, this error, this residual should become 0 if I integrate this over this complete domain. So if we are talking about only the first order trial function, then we have only one term in this, and the residual will be in that case x and function of this constant this. If I integrate this over the domain with respect to x, then it should be equal to 0. So this is our main equation that will give us the value of a1 such that this condition is satisfied. And once we get this value, now our solution, we can substitute back into our assumed solution, that is phi dash. For first order it was a1 n1x, and n1x we have already assumed is a trial function. So particular method is there for trial function, and that one condition should be satisfied, that it should be continuous and it should be differentiable up to the highest order present in the governing equation. So this particular method, we can take a simple example to understand this method. An example of the heat transfer equation, d2t divided by dx square plus 1000 x square is equal to 0, where this x is less than equal to 1 and greater than equal to 0. And the boundary conditions are given as, t 0 is equal to 0 and t 1 is equal to 0, and it is also given that we can use the trial function as x1 minus x square. So it should be continuous and differentiable, the trial function, up to the highest order present in this case. So that is why we have taken this trial function. It is given, otherwise we can say it is given in the problem, though we have different methods in finite element method that we will be discussing later on, how to evaluate the trial functions, how to select a trial function, how to find the expression for the trial function. But right now we are not using. So we assume that this is our problem statement, that we are given with some governing equation. boundary condition and trial function is given. Now we have to solve this equation with the Ritz method or approximate method. So the t is the field variable, so now t dash will be equal to a1 n1 x, or it is equal to a1 x1 minus x square, or t dash I can write down as a1x minus a1 x cube. If I substitute this in the differential equation, we get residual. So if I substitute this d2 t dash divided by dx square plus 1000 x square, this will be equal to nothing but some residual. It will not be exactly 0, and this residual will be function of x and a1. So now it is simple that we can find out, we know this expression, so I can find out what is the second derivative of this function. So if I differentiate this once dt over dx, I will get a1 minus 3 a1 x square, and if I differentiate it again, I will get d2 t dash divided by dx square, that is equal to minus 6 a1 x. So now we have the value of this. I can substitute here in this case, and I can get the value of residual, that is residual x a1 is equal to minus 6 a1x plus 1000 x square, and our value is the domain. In this case we can say domain is from 0 to 1. So now I have to integrate this, because our aim in this case is to integrate this residual that we get from over the domain, and that should be equal to 0, so that we get the approximate result of the problem. So I integrate this 0 to 1 over the domain x entire x, and the expression is r x over a, and this I am directly substituting here. It is minus 6 a1x plus 1000 x square dx is equal to 0. Now you integrate this and tell what is the answer. So if I integrate this, I get minus 6 a1 x square. So we get minus 3 a1 plus 1000 over 3 x is 1, and this will be equal to 0. So we get value of a1 is equal to this minus minus will cancel, and it is 3 and 3 is 9. So it is 1000 by 9. So a1 we get 1000 by 9. So now I can get my answer. The solution is t1 dash x is a1. Where is this t1? It is a1x minus a1x cube. So I can take a1 out, that is 1000 by 9 into x 1 minus x square. So this will be the solution of this particular equation that we have started with, and this solution is approximate one and is known as Ritz approximation. Thank you all the viewers for attending the session. Thanks a lot.